Hey everyone, Big Mac here. Welcome to another QualQuest video. So today, this is what we have. We are given some smooth function on the bound from 0 to 2, that's our domain, and we're also given that every derivative of x is less than 1 by absolute value. So again, that coincides with our notion of a smooth function. Lastly, we are given the evaluations of the functions at the points, at the points 0, 1, and 2. So first part of our problem is just to find the second degree polynomial which matches all these parts. So to solve for this, we can either do it one of two ways. The most standard way to find coefficients of a second degree polynomial would just be to set up a system of equations and then solve for our unknown variables, a, b, and c separately. Yeah, sorry, I keep tilting it. Other version we can do is we can write the Lagrange polynomial, which includes a summation of a product. So this is where the x to our power part comes from. This is where our different coefficients come from, and then we also include our evaluations of the functions at that point. I'm just going to use the bottom one and show you the answer. So here I just went ahead and carried out all the terms. Go ahead and pause if you need to look at the work a little bit more, but I'm going to the next screen. Alright, so just carrying out our terms a little bit. This is the second order polynomial that we collect. So we're going to use this now to solve the rest of the problems involved with our question. So the first thing that we're asked to do is to estimate our integral of f of x from 0 to 2. Obviously we don't know f of x, so that's why we have to use our second degree polynomial as our estimate. So again, we just go ahead and normally do our integration by parts, or not by parts, we just do our term-wise integration. We know all the coefficients already, those were our coefficients in front. We evaluate between our bounds. We clean up our terms a little more nicely down here, and down here is where we get our answer. We get 1/3 times our evaluation at 0, plus 4/3 times our evaluation at 1, plus 1/3 times our evaluation at 2. And this should not be a surprise, because this is the exact same estimate you would get using Simpson's method. The next thing we are asked to do is to give an upper bound difference from our original fx. So, how close how close is our second degree polynomial an estimate of our actual original function? So we can use this formula here. For a given polynomial up to degree n, we take 1 over n plus 1 factorial times the nth derivative of some point z within our domain, because we don't actually know where it is, but it's got to be in there somewhere, times the product of our x minus our domain points, which were 0, 1, and 2 in this case. So 1 over 3 factorial is just 1/6. We would need to find a bound on the third derivative of our magical point c, but like we mentioned at the beginning, we know that our function is smooth and that all of our derivatives are bounded by 1 in absolute value. So that part goes away. Then we just multiply these parts out and we have our x cubed minus 3x squared plus 2x. So again, we have absolute values on the inside, or on the outside. So whatever our value x that we plug into here will tell us how far we're away from our original function f of x. Alright, and now for the last part of our problem, we wanted to find an estimate on our total integral function, f of x minus p2 of x. How close is our whole integral with respect to our original function? So again, we just take our difference function where we had our absolute value. Here's our x cubed minus 3x squared plus 2x. We have 1/6 on the outside. Again, integrate this from 0 to 2. Only thing we have to pay attention to is, since we have an absolute value notion here, we just need to break it up between when a function is positive and when it's negative. So this is just a basic graph of the function. So it's positive from 0 to 1 and negative from 0 to 2. So when we evaluate this integral, we need to take the positive integral from 0 to 1 and then subtract the integral from 1 to 2, since we're looking for an absolute value. Basically, if you evaluate all your terms, the first half you're going to get 1/4 times your 1/6, so 1/24. On the other half, when you take the antiderivative and evaluate it 2, all these terms are going to cancel out, and all you're left with is a negative 1/4. And since we're doing a negative integral, we have the two sides cancel out, so we have 1/24 on this side as well. So we have 2/24, or 1/12, which means that our second-degree polynomial in this case for a very good smooth function is no more than 1/12 off the actual integral. So that's a definitely useful tool for some numerical values. Okay, Big Mac saying, hey.